In section 2.5, we're going to, we'll do a little bit in section 2.5. Let's stop talking, please. We'll do a couple of days in 2.5. We'll do a little bit today. We'll have some extra practice tomorrow. So I'm going to call this logic and proof. So like I mentioned back maybe in chapter 1, we talked about Euclid and the elements and how it was really one of the first times that math, something in math had been built using just logic. And the reason we're doing this is it's really the only time in math where you, in high school at least, where you learn to use logic a little bit to say why things that you think are true are actually true. Now what Euclid did was he took 5 postulates, he called them common sense statements, so those are the postulates, and 23 definitions. And using logic, using deductive reasoning, sometimes inductive reasoning, but then you have to prove things, built everything we know about geometry from those 5 postulates, 23 definitions. Not a lot of information. So what we're going to do is start to use logic to write proofs of things that we think are true or that we know are true. We're just going to say why we know they're true. All right. So the first way we're going to use proofs, we're going to kind of just dip our toes into the water a little bit, is with solving equations. And we're going to talk about properties that tell us why we're allowed to do the things we do when we solve equations. So these are, the first thing we're going to do is talk about the properties of equality. So these are things that we know that we can do. So these are kind of like our postulates for solving equations, really. So properties of equality we use for numbers and equations. And we'll talk about some different kinds of properties in a little bit. Addition. And I'm not going to write addition property of equality. All of these are properties of equality. So the book will always say addition property of equality. We'll just say addition. That's fine with me. So all of these are properties of equality. The addition property tells me that if A equals B, then A plus C equals B plus C. I can add the same thing to both sides of an equation. That's what the addition property tells me. The subtraction property. Same starting place. If A equals B, then A minus C equals B minus C. I can subtract the same thing from both sides of the equation. The multiplication property. If A equals B, then AC equals BC. I can multiply both sides of the equation by the same thing. And then the division property. If A equals B, and we're going to say that C is not equal to 0, we don't want to divide by 0, then A over C equals B over C. I can divide both sides of the equation by the same number. So these are the properties we use all the time when we're solving equations. And so we're just writing them out as kind of a rule. And when we do these proofs, we're going to say, okay, I'm going to subtract something from both sides of the equation. The subtraction property tells me that I can do that. That's the property that tells me I'm allowed to solve an equation by doing that. And when we do a proof, all we're doing is listing what we're doing, and then we're listing why we know that we can do it. All right, we have a few more properties. These are the ones we use a lot. Substitution we also use. If A equals B, we can substitute A for B in an equation. So the substitution property tells me that I can plug something in place of something else that is equal to it. So these are the things that we use a lot when we solve equations. We also have a couple of properties that let us rewrite equations and rearrange a little bit. The reflexive property says any number equals itself. A equals A. The symmetric property says if A equals B, then B equals A. Doesn't matter which order I write this in. I can turn it around. And we do that a lot when we're solving equations. We have x on the right-hand side, and we want to put x on the, we want to flip the equation around. We have 25 equals x, we can write x equals 25. The transitive property. The transitive property is like the project we did, sort of like the project we did in class, where it lets us link things together. So we're going to say if A equals B and B equals C, then A equals C. So I'm linking A equals B, B equals C, so I can say A equals C. I'm linking the first thing to the last thing. So it's like our project is like the law of syllogism, sort of. Same kind of idea. I linked some things together. And we also have the distributive property. A times B plus C equals AB plus AC. So I can distribute that A inside the parentheses. And I can also do that with subtraction. And we do use distributive property sometimes when we're solving equations. We have to distribute. All right, so these are the rules, these are the properties, these are kind of our postulates for solving equations. So what I want to do is do an example, and we're going to go through the steps of solving the problem, but every time we do a step, we're going to list why we know we can do that step. What property tells us that that's what we can do to take that next step in our solution. So when we construct a proof, when we make a proof, we start with something we know, and then we figure out step by step what other things must be true, and when we do a proof, we say why we know they're true. All right, so let's look at an example. Questions before we go on about our properties? Okay. So here's my setup. Problem like we've done before. We just want to, what we call justify every step we take. So we want to find x. So the first thing we do is we say, what do we know about this situation? What do we know about those two angles? They add together to equal 180. So I'm going to say my first step is x plus 2x minus 15 equals 180. So this first reason The reason we know this is true has to do with geometry. So how do we know that's true? Right, so a line equals 180. What did we call two angles that made up a line? We gave them a special name. Complementary means they add to 90 degrees. They're supplementary. What did we get? So, but we gave that pair of angles that make up a line. We gave them a special name. Linear pair. So I'm going to say the reason we know that's true is linear pair, and we know that a linear pairs are supplementary. And that's just a fancy way of saying what Fabian said, they add up to 180 degrees. All right. Now we're going to find x. What would be our first step here? What would we do if we were trying to solve for x? Combine. So I'm going to say 3x minus 15 equals 180. So now we need to say why we can do that step. What do we call doing that process? Combining the x and the 2x? What kind of terms are those two? Like terms. So I'm just going to say combine like terms. Sometimes the book will call that step something a little different. If you called it combining like terms, you would be fine. All right, so what's our next step? What did you say, Alex? Add 15 to both sides. So I'm going to write in red. A lot of times in the book, they won't write the plus 15 like I write it here. So I'm going to say 3x equals 195. So they would go straight from here to here. What tells us we can add 15 to both sides of the equation? Addition property. And if you just said addition, you'd be fine. So I just said addition property. All right, what do we do next? Divide by 3. So I'm going to write this here. A lot of times when you see these things in the book, they won't show you that this division by 3, and they'll just say x equals 65. What tells us we can divide both sides of the equation by 3? Division property. So that would be the steps of solving that problem and listing why we know we can do those steps. All right, questions there? So tonight's homework will be similar to, you won't have to construct this from scratch necessarily, but they might give you this and then give you this and say, how do you know you can do that? And you'd say the addition property. I'm adding the same thing to both sides. All right, so the properties of equality are for numbers and for equations. We don't add and subtract shapes, so we need properties of congruence for shapes. There aren't as many of these. So our properties of congruence. And these are for shapes. They have similar names and they work kind of the same way. Our reflexive property, and the book would say reflexive property of congruence. What reflexive property says is figure A is congruent to figure A. A shape is congruent to itself. That's what the reflexive property says. Figure just means any kind of shape. Could be a segment, could be an angle, could be a square, could be a pentagon. So a shape is congruent to itself. The symmetric property. Symmetric property says it doesn't matter what order I write these in. If figure A is congruent to figure B, some kind of shape, then figure B is congruent to figure A. So I can turn those around. Doesn't matter which order I write it in. Doesn't change the fact that those shapes are the same size and shape. And the last property of congruence, transitive property. And transitive property, just like transitive property for equality, lets us link things together. So if figure A is congruent to figure B, and figure B is congruent to figure C, then figure A is congruent to figure C. So it lets me link this first one, A to B, B to C, so that lets me link A all the way to C. That's what the transitive property does. Lets me link things together. All right, and we use the properties of congruence for shapes. Properties of equality we use for numbers and equations. Properties of congruence we're going to use for shapes. All right, questions on these properties? Okay, so what I want to do is do a little practice using these properties, and then I'll show you how we put them together to make a proof. All right. So these first examples, which property are we using to do this? We'll just do one step here. So we're going to go from 7x plus 3 equals 24 to 7x equals 21. So what did I do there? Subtracted 3 from both sides. So what's my property? Subtraction property. So let's just say, what did we do here? We did subtraction. How about I'm going to say RS equals ST and ST equals TU. So RS equals TU. All right, before we answer this question, let's remember what is RS? What is ST? What are those things? When I say RS is equal to ST, what am I saying? What am I saying are equal? What is RS? So if it had a bar over it, it would be a segment, right? Without the bar over it, what does it tell us about the segment? What do we do with segments? How do we compare them? They can be congruent, or what can be equal? If segments are congruent, what's equal between them? The length. When we write two points without a bar over the top, that's talking about the length of a segment. So this is saying the segment length of segment RS equals the length of segment ST. The length of segment ST equals the length of segment TU. These are lengths of segments. So what property says if RS equals ST and ST equals TU, then RS equals TU? Transitive property lets me link these things together. So this is the transitive property. All right, one more of these. 5x equals 10, and then I wrote that as 10 equals 5x. What property am I using to do that? Reflexive property says something is equal to itself. Which property lets me change the order? Symmetric property. Symmetric property lets me change the order. So the symmetric property lets me turn this around. So what we're going to do in geometry, starting today, we'll do it kind of start really slowly, but as we go through the course of the year, we're going to do this more and more, where we prove things. We know something is true. We want to prove that some other thing is true. So a proof is an argument using logic. So we start with something that we know is true, and we figure out what else must be true. We use a proof to show a conjecture is true. And let's remember what a conjecture is. That was from the very beginning of the chapter. When we make a conjecture, what are we doing? I look outside and I say, it's sunny, I think it's warm. So my conjecture is it's warm outside. So conjecture is we're saying what we think is true based on observation. A proof shows that a conjecture is true. So we're using logic to show that a conjecture is true. What we're going to use mostly in this class, it's not the only way to do a proof, but it's called a two-column proof. So a two-column proof means on one side we put our statements, and on the other side we put our reason. So if I go back here, that's essentially what we did here. Here are our statements, and here are our reasons. So this is kind of a two-column proof. So here's what we're going to prove here. I'm going to do an example, and here's my setup. Now to start, you all won't have to do a proof from scratch like this. Usually the proofs are set up where you fill in some blanks in the proofs, but eventually you'll be able to do something like this. All right, and we are given proof. We start with some information. The given information is what we know. So we're given that AC equals BD. We want to prove that AB equals CD. So here's AC. And here is BD. So we know that AC equals BD. We want to prove that this shorter segment is congruent to this shorter segment. So let's start out with what we're given. We don't always start with what we're given, but often we do. And my reason here is this is given. All right. So what do we know? We don't have a lot of information here, but we know a few things. From the picture, what do we know about segment AC? Isn't it made up of two smaller segments? Isn't AC made up of AB, segment AB, and segment BC? Yeah. Yeah. And isn't BD made up of segment BC and segment CD? Yeah? So let's write that down. I'm going to say that AC equals AB plus BC, and BD equals BC plus CD. So thinking back to chapter 1, what postulate tells us that we can add two smaller segment lengths together to get a bigger segment length? One of the first postulates that we talked about. This is the segment addition postulate. The segment addition postulate tells us we can add two smaller segment lengths to get a bigger segment length. All right, so let me use a highlighter here. Here is AC. And this tells me that this is the same as AC. And here is BD. And this tells me that this is the same as BD. So what I want to do is I want to take this and put it right there. And I want to take that, and I'm going to make that blue. I want to take that and put it right there. Since those are equal, I can substitute one for the other. So I can say AB plus BC equals BC plus CD. So what do we call it when we take something that's equal and plug it in? Substitution. I substituted this for this. I substituted this for this. So this is substitution. All right, and these are segment lengths. These are all just numbers. So I have this number BC, whatever it is, on both sides of the equation. What can I do with that number BC on both sides of the equation? I want to subtract. I want to get rid of it because I'm trying to get AB and CD. There they are. I want to get those by themselves. So I'm going to subtract BC from both sides of the equation, whatever it is, 12, 7, whatever that happens to be. Subtracting that from both sides of the equation. Subtraction is what tells me I can do that. And I got to where I was trying to go, at AB equals CD. So this is how we put together a proof in geometry. Now, at first, we're not going to expect you to do this all from scratch, but if we had a blank here for substitution, if we had a blank here for segment addition postulate, we would expect that you would be able to figure out that that's what's going on in those things. The first proofs that you'll talk about have to do with solving equations and talking about addition, subtraction, multiplication, division, that kind of thing. And then we'll start doing more with geometry and shapes. All right, questions? Okay. Homework?